So good afternoon, everyone. So today I'm gonna talk about high-performance fiber reinforced concrete, and quick review of the key benefits, especially on the sustainability side. That we did more work on that. Some review also the best practices to do mass production of this fiber reinforced concrete. And I will get to two case studies that we have been doing in Eastern Canada. So first, when we look at what is actually high-performance fiber reinforced concrete, it's simply the combination of high-performance concrete properties where we expect to get higher durability, higher strength, higher performance overall, and we combine it with the addition of discrete fibers reinforcement. So we expect superior macrostructure, superior matrix, and this is important to keep in mind, especially when we're gonna select the type of fibers, because we want to maximize the synergy between both. And like for UHPC, it's an important point. So when you look at one of the two key benefits, the first is it provides superior structural efficiency. And how? So by the addition of discrete fibers, we are able to improve the flexure and the cracking resistance of the concrete, but also we provide a superior resistance to exposure conditions. And this is a bit different than just providing high strength concrete. We will see later, especially in Canada, exposure condition can be harsh in terms of freeze-and-thaw and south exposure. So that's the combination of the two. So it typically, ultimately, will provide a longer service life. Now, when we want to map out where high-performance fiber reinforced concrete land compared to regular fiber reinforced concrete in UHPC is right in the middle. So typically, as the structural efficiency increase on the top right, and as the exposure condition on the resistance or the durability of the material increase also, we get a stronger, better material. And ultimately, on the top right, we have the UHPC. So we work on the microstructure, we work on the interaction with the fibers, and we want to maximize the synergy. And we look at also the durability aspect in terms of penetration to chloride or freeze-and-thaw resistance, for example. In terms of sustainability, because we provide superior structural efficiency, this leads to less reinforcement, potentially reduced section using less material. On the other side, because we provide higher durability, we can expect longer service life and lower maintenance. So both together lend to a superior sustainability concrete solutions. Now, how we can capture that benefits in terms of LCA and for this material, but this is true for any fiber reinforced concrete. So I don't know if you are familiar with the whole building LCA. So typically is to run the analysis not at the material stage, but on the whole building, on the whole structure. So the first step when you do that, you do material inventory. So you look at how much material you have on your structure in terms of cubic meter of concrete, amount of fiber, amount of steel, and so on. And then you multiply that by the respective carbon footprint, right? So when you have superior structural efficiency, that means you're going to need normally less material, less reinforcement. That's where you're going to use it. If you stick to just the carbon footprint per cubic meter, you won't see the benefits of the fiber reinforced concrete. So it's very critical that we extend our scope from the material to the whole building onto the whole structure. In terms of durability and improvement on the service life is the same. Normally, we should see when we run the scenarios on the maintenance, on the repairs, on the long term, we should spend more but also it should cost less in terms of carbon footprint. Same thing for the scope. By extending, if we want to capture the impact of this material on not only on the product itself, not only on the concrete per cubic meter, we need to look at the other scope. So typically the repair stage, the in-use stage, and the operation carbon also. One point here for the end of life and for circularity for fiber reinforced concrete. This is not something that we have a lot data so far. That's something I think we need to work on the future. For concrete, it's pretty clear. We are able to recycle pretty easily the material. On the fiber side, on fiber reinforced concrete, we can do it, but there is still some work to do on that side. The other thing is, if you really want to capture the impact on the service life, is to increase what we called in LCA the reference duty period. So this is equivalent as the service life period. So typically on the graph, you have the cumulative carbon footprint. The blue is the embodied carbon. This is for building, but that's the same principle for infrastructure. And the orange that is built up year over year is your operation CO2. So you can imagine typically for buildings, the LCA is run for 60 years. If after 60 years you need to tear down the building and rebuild it again, you come on the top and you add it. From the get-go, if you design with high-performance fiber reinforced concrete or UHPC, you may have a higher upfront embodied carbon, but on the long run, on the 200 years, on the 150 years, for example, service life will get a better footprint. So, quick review of the best practices to ensure how we can make mass production of fiber reinforced concrete. So typically from the lab to the production. So first, in terms of mix design and the key levers to maximize the synergies between the fibers and the matrix, the first step is to look at, based on the durability requirement and the exposure conditions, do we need SCMs? Do we need air entrainment? Do we need how we can play with the water cement ratio and the porosity of the matrix to increase the durability? One key aspect, especially when we use high dosage of fibers, is we need to work on the aggregate gradation to make sure that it's properly integrated, especially if you have to pump the mix. And as I said, as you get stronger and stronger matrix, you need to be careful and mindful of the fiber tensile strength and shape, because you can end up to what we call embrittlement. So typically you can have a snapping, your fibers can snap. And the last piece that is important is the rheology. So you need to have a stable mix, especially if you have air entrainment. You need to have something that is stable from the plant to the site. So I reviewed quickly the typical application for high-performance fiber reinforced concrete. For now, is mainly in the precast. We see some application on the cast in place, but I will say is mainly precast. In terms of QC/QA, is the same deal as we get higher performance, we need to get tighter and tighter in terms of how we control our material, how we control our batching process. This is to ensure conformance, but also to minimize the variability of the performance. One key aspect, especially as we get lower and lower water cement ratio, the batching, the sequencing, to ensure we have a proper dispersion and the proper hydration of your matrix is critical. And how we coach our drivers and how we cure the specimen, it's more and more critical. So basically, we are first example I'm presenting. So this is a repair we had to do on a high performance concrete column. We had to do a jacketing. And for that, the exposure condition was high in chloride. So in Canada, we use the class that is called the CXL. So it's highly exposed to chloride, saturated, and with freezing total exposure. Because we have a repair, the other component is we have highly restrained shrinkage condition. So you need to work around how can you reduce the stress and increase the compatibility of the repair. So for that, we have a 50 MPa mix. We use an SEC consistency. We added some fibers. The fibers, what it does, it's also bring down a little bit your MOE, your modulus of elasticity. So it makes it, a little bit more ductile, but less brittle when between the repairs and the core material. So we have been able to achieve pretty good consistency on this project. We also implement maturity to have early stripping and early curing, because we integrate some shrinkage compensating admixture. And when you add this mixture, it's critical to add early curing, wet curing. And that was a good success. The last one is, this was a challenging one, was 70 MPa concrete with air. So 5 to 8% air, combination of steel fibers and synthetic fibers for precast elements. So same thing, high exposure condition, high strain gain was also required, and the delivery time between the plant and the job site was about 2 hours. So, and we were because the concrete was pumped, the air void system was tested before and after. So this was the challenging part, where we had to babysit a little bit the site and the mix to ensure we have a very, very stable mix, especially when you have fibers. Same thing, we integrate also maturity for early stripping with good curing practices, but a very heavy QC/QA on the process. So to conclude, so this high-performance fiber reinforced concrete, it provides a lot of benefits on the structural and sustainability side, mainly by improving the durability and by improving, being able to reduce the amount of reinforcement. Provide also a very good cost-effective solution and a speed. It's also, you can produce it in mass production if you have a tight and a QC/QA protocol and good expertise. This is mainly not only in the lab, but is really in the production. You need to work very closely with the operation and with the customer to ensure you have proper curing also. This is fundamental. And the last piece, I think, this material is, the benefits of this material is undervalued in the industry, and I think we are working strongly with different technical committees here, the 544 or the 239, to improve the visibility of these benefits, and we need to gain more traction, especially on the sustainability side, regarding this material.